Hello, everyone, and welcome to Facet Nation, a Gemmology podcast. I'm Lucinda. I'm not going to be able to rap for you like Simon did last week, but we're very happy to have you here.
I'm disappointed about that. And in case you don't know, which you should by now, I'm Simon.
And we're both FGAs, and he's also a DGA, but we stopped saying that because we don't want to toot our own horns.
You don't want to start showing off too much. Although we did just graduate, so
and it was really nice. It was a nice.
That was really
evening.
fun. Yeah, it was a really, really lovely evening, and there were some lovely people there, and it was really good.
Yeah, it was lovely. I was prepared to be disappointed, but I wasn't. I thought the food was great. There were these prawns.
Yeah, no, I thought the whole thing was really nice. I thought it was going to take like forever as well, and it didn't seem to be that bad, actually.
No, it wasn't bad at all. It was really nice.
No, really good.
So, highly recommend.
One of the other people that graduated from the Diamond Diploma and also won the Bruton Award was Judy.
Yes.
And Judy's been in touch with us this week because she has solved she's one of two people that have solved the issue that we had with the mnemonic for the Mohs scale.
Which, if you guys don't remember, our version is a bit weird. So it's the girls can flirt and other queer things can do.
Which we don't like. It's not giving good. It doesn't. That's not good. So we wanted to move away
very
from that.
1950s to me.
Yeah, and we put out a call for you, our listeners, to tell us some other options. And we've had a couple this week, which are more or less the same, just with slight variations. Do you have them written down, or would you like me to go over the pair that we got?
I certainly do not have them written down, Simon.
Fine. I'll take care of that then. So Judy's offering was the ginger cat found an old quilt to cuddle delightfully.
I love that.
Which she followed with cat mums unite.
If you know, you know.
So yeah, that's number one. And the other one, which came from our new friend, which we finally got to meet in person, which was Daniela. And she had the good cat found an old quilt to curl down.
Oh, I like that one too.
Yeah.
I like that there's all these cats involved.
You don't have to say delightfully at the end, which is a bit of a mouthful at the end of the mnemonic. So
I don't know.
Maybe I prefer that one.
I think
Cuddle
I prefer Judy's.
Delightfully is quite a mouthful at the end.
Yeah, but it feels like something I would actually say.
Cuddling delightfully.
Different strokes for different folks, Simon.
Okay, well, yeah, so everybody that's listening can tell us which one they like the best and start using that to remember the Mohs scale. And right on cue, there's a cat.
This one's
curling down or not,
delightfully.
As the case may be. Yes, delightfully, yeah.
Thank you for showing up on your bet, Francis.
What are we doing this week?
Well, this week is actually, I thought it was going to be a tough one. It is scientific, but I think you guys are going to really enjoy it. And it may feel like a little bit of a departure, but I would say we're taking a tiny detour to understand a concept that is going to come in really, really helpful and be really crucial. Today, we are starting our light and optics journey, and we're starting with waves and the history of light. So before we tell you all the things you need to know about light, we're going to sit down and figure out what the fuck is light.
Yes, I, for one, am very excited by the whole thing.
I know you are.
There's lots of famous scientists that we are going to tell you about.
Lots of theories. And guys, some of this you do need to remember, but I think the whole thing, Simon put together these notes and they're really lovely because it really humanizes the whole journey of light and how we understand it. And also brings up some terms that maybe you've already started hearing and are confusing a little bit. Maybe they're not totally clear in your mind. And so we're just going to lay it all out there. What is light? What has our understanding of light been historically? And how does it interact with the world around us? Because it is kind of crazy, like how much relies on light.
Absolutely. Like, yeah, you wouldn't be able to see anything if it weren't for light. Like your eyes don't work unless light is interacting with the matter in front of you. So
color doesn't exist unless there's light involved. It just doesn't
does
exist.
Not exist. No, none of those things, color, luster, transparency, all your optical effects, none of them exist. So all of your gemstone related things, the important things, rely on light, and pretty much you being able to see anything relies on light. So it's important to get this history and this information as a good grounding for investigating light in terms of gem testing and gemstones and what makes them what they are.
Especially as we start getting into the stuff that feels really dense, really heavy. So why does your polariscope work? Why does the refractometer work? It all makes so much more sense if you can visualize what light actually is and understand how it's moving through the world.
Yeah, exactly. It's really important to know how it works in order to understand how those things work.
All right, so let's get the ball rolling. So Simon, what is light?
Well, let's get into it, because basically we have vibrations and waves is how we will start telling you about light. And light is widely regarded to behave as a wave. So we're going to take you through what a wave is, basically, to begin this. So the simple answer to what a wave is the ripples that you see on water if you drop a stone in it, for example. These ripples are waves. Yeah? And a wave is a disturbance that travels through time and space, which carries energy. And this disturbance is a repeated vibration. So if you attach a rope to a wall and you shake it once, that's a vibration. But if you keep shaking it, then those repeated vibrations become a wave.
And if you guys have ever done that exercise in the gym where you have to shake the ropes, have you ever done that, Simon?
Yeah, what are they called? They've got like a name.
I don't actually know what they're called. It's always part of like HIIT workouts, but you can kind of feel them. They take on their own kind of energy.
It's really hard to get them going, but once they're going, they sort of like the motion. You just have to,
exactly. They almost
you have
do
to
it for you.
Maintain the motion, don't you? Yeah.
Exactly. And so lots of things in our universe work this way. And there are two types of waves. So we have the longitudinal and the transverse. So longitudinal waves vibrate in the same direction that they travel. So an example of this would be sound waves, and transverse waves, which are the ones that we're concerned with, travel perpendicular to the vibration. So how can we visualize that a little bit, Simon?
So, yeah. If you imagine a wave traveling across water in front of you, so it's going from left to right, east to west, that is the direction of the wave. So the wave direction is going left to right, or east to west, as it were. That's the direction of propagation. Yeah. So remember that term. Direction of propagation is the direction in which the wave is traveling. Now, the vibrations are the ones at a right angle, so perpendicular to that, and they go up and down, so north to south. So this would be like the water molecules moving up and down when you see the ripples. The molecules themselves aren't actually moving anywhere in terms of distance. They're just sort of like vibrating up and down. Yeah, and this is basically how light waves behave.
Now, when we talk about waves, we're talking about something with a few different characteristics. So these are some words that you're going to hear us saying. We're going to go into each of them, so do not panic. Just try and really take them in. So we're going to talk about amplitude, period, wavelength, frequency, speed, and phase. And so you might remember from school in your trigonometry lessons, sine and cosine. I do remember that, but I remember the words, but have totally blocked out the rest of it, which is fine because we don't necessarily need to know it. All we need to know is that light waves are sinusoidal. So imagine the letter S rotated at 90 degrees, and then there's a line through the middle of it. So it's like a dollar sign on its side. This is a sinusoidal wave. The curve is smooth and it oscillates above and below that central line. So we're not talking about the highest point to the lowest point. We're talking about any point to that middle. That middle is where we like to measure things from.
Yeah. So, the distance between the mean value, the middle line, and which is also referred to as the rest position, and its maximum, so its peak or its crest, and its minimum or its trough would be the amplitude. So it's that middle line, the line going through the S or through the dollar sign up to the top or down to the bottom. That's how you describe amplitude. So it's not the top to the bottom of the wave. That would be double the amplitude. It's from the middle rest point to the peak, if you like, or the middle rest point to the trough.
I really like the term rest point because I think that makes it as clear as it can be. Like we have an equilibrium and then we're going up and we're going down, but we're always coming back to this equilibrium. And it does logically make sense when you think about it, that if something's going way up, that is more energy, more brightness, and then coming back down to rest. So it does make sense in its way. We also have, period is the interval or the amount of time essentially between the beginning and the end of a full wave cycle. So how long does it take to create that full S? So from crest to crest or trough to trough, how long is it taking to make that full cycle?
Yeah, exactly right. And then there's the wavelength. So the wavelength would be the physical distance between two identical consecutive wave positions. So again, that's like the crest to the next crest, or the trough to the trough, or the beginning of the S to the end of the S. And this is in waves measured in meters or subdivisions of meters. In the instance of light waves, we're talking nanometers. Yeah, they're very, very, very small. So a nanometer is 1/1000th of a meter. So yeah, we're talking like really, a meter, and then 1/1000th of that is tiny, tiny, tiny. And to put this into context, a human hair is about 80 to 100,000 nanometers thick.
So very small, basically.
Yeah. But the visible light range is 400 to 700 nanometers. So 400 to 700 nanometers is the light range, and a human hair is 80 to 100,000 nanometers thick. So we're talking so small.
And then we also have frequency, and this is the number of oscillations or full wave cycles during a set period per second. So this is pinned to time that you can tell, right? Something that you can see on your watch, but it's measured in hertz. So 1 hertz equals 1 wave per second. So if you have a high frequency, you have shorter wavelengths, higher energy. This is where you start to get worried about, like, is something going to irradiate your DNA? And then low frequency is longer wavelengths, less energy, more relaxed. But the amplitude doesn't affect this at all.
No, which is interesting, isn't it? Because you'd think if the peak were higher, it would basically take longer, but it doesn't. This doesn't affect that. So the amplitude affects the brightness or the amount of energy. It doesn't affect the frequency of the wave, which seems counterintuitive, but it's true.
Physics. Great.
Physics, indeed.
Now, this next, I guess, discussion term, interference, this is one that you guys may have already been seeing, already been hearing a lot. So let's get to the bottom of what interference actually is. When you see it, you may recognize it as this kind of like rainbow, but it's actually something's causing it, something very distinct. Simon, take it away.
Yeah, so interference is when two waves are in the same place at the same time. So there's two types of interference. There's constructive and destructive. Now, constructive interference is when two waves are perfectly in sync. Yeah, so like the crests align with the crests. You've got two waves, they're in line. The crest and the crest is together in line, and the trough is in line. This produces amplification, and the wavelength gets brighter.
I always like to think of this as, you've got a sister, don't you, Simon? Like
I do.
Siblings. When siblings are getting along really well, everyone's personalities are kind of amplified. Like everybody is a bigger version of themselves, especially out in public. Everyone is a little bit funnier and like so much more themselves when you're getting on with your siblings. That's constructive interference. When you're not aligned, when you're fighting, this is destructive interference. So go and tell us about that, Simon.
Okay, so destructive interference is when the crest of a wave is in line with the trough. So if they're completely out of phase, they're going to destroy each other effectively. They cancel each other out. Yeah. So let's say the peak of the wave, let's give it a numerical value. So the peak would be +5, and then the trough is -5. So if you have +5, take away 5, you've got 0, and that gets you back to that rest point. So if you've got the rest point, then nothing is there. Yeah. And then all of the different synchronizations in between these two values basically affects the amplitude, but not so that they perfectly sort of double like they would if they were completely in phase or completely constructive, and they don't completely cancel each other out, so they don't sort of disappear. So if a wave is going to be aligned in this way, it's said to be in phase and must peak and trough in perfect synchronicity with 0 phase difference. These waves must have the same wavelength and frequency to remain in phase for any extended time period.
I love in phase. And this is something, so in phase, out of phase, these are phrases that you'll hear us throw around, especially as we start getting into optical effects. We start talking about labradorite, thin film interference. Opals are another one where this is really important. So really good to just kind of practice in phase, out of phase. Think about it. It does make sense. And that's how light waves are characterized. So let's explore how they behave, because ultimately light has a wave function. And so when you look at, sorry, I just talked myself into a corner there. I have no idea where I was going to go next. I got distracted thinking about light waves as siblings.
No,
okay,
this is all important stuff, because these are the things that help people memorize things. Like our friend that messaged us the other day when we got an email from him. He says he really likes it when you refer to like the bad girls and the cool girls at school. So thinking of waves being in phase as siblings, then this is what people are here for. It all
comes back to high school, guys.
Yeah, this is what people are here for.
So we've got our light. We've got our light rays. Where is it coming from? Usually the sun. So let's say it's coming from the sun. There are billions of light waves vibrating in every direction perpendicular to the direction of propagation, and that's happening all around us. So if the wave is propagating towards me from the sun, for example, there are waves vibrating left, right, up and down, diagonal, like there's a gajillion of them, and they're all going their own way. They're all doing their own thing. That is unpolarized light. There is no order or rhyme or rhythm to the vibration directions. This light is not always helpful to gemmologists, but when you polarize that light, suddenly it becomes quite useful. So Simon, tell us about polarized light.
So polarized light is basically when all the waves vibrate in just one direction. So polarized sunglasses work on this principle. So when sunlight is reflected off a reflective surface, the waves become polarized and they vibrate in one direction. So a polarized pair of sunglasses have a filter in them which block that particular vibration or orientation of vibration, and therefore the light reflecting off these reflective surfaces, or glare as we like to call it, is then reduced. So I didn't know that that's what happened. Someone said, "Oh, would you like your lenses polarized?" And I was like, "I don't really fucking know what that means." I know it
also,
like
shout
reduces
out to
glare.
The people who figured this out, right?
Well, yeah, but useful stuff. So if you're like driving along the road and there's, it's been raining and then all of a sudden it's sunny, and the light reflects off the water on the road. Well, if you've got your polarized sunglasses on, then those particular vibration directions aren't getting through. They're not getting through your lenses. So, yeah, big up the Ray-Bans.
And very much the same kind of thing is happening in anisotropic gem material. So Simon has told us, imagine you're sitting inside a ruby. So everybody close your eyes. We're sitting inside a ruby. When light comes into the stone, into that material, it's vibrating in all directions. But as soon as it crosses into the ruby, it is split into two rays. So one is vibrating exactly left to right and one exactly up and down, for example. That is because these rays are now plane polarized. So we're going to talk a lot more about this. Don't worry, there's a lot to go. And obviously it is all of this is utilized in your gem testing equipment. This is so much of what we're testing is how is light interacting in a material as it passes through. So get excited about that. But for now, we are going to be looking at other important behaviors of waves, which it's pretty important to get straight. Some of them are pretty obvious, but there's a couple that you can mix up.
Yeah, so these are the ones that we're going to explain in more detail when we're talking about like gemstones and how some of your testing equipment works. So it is very important that you get these behaviors of waves down. So you want to be learning this. Now, the three different behaviors of a wave are basically reflection, refraction, and diffraction. And now we're going to explain to you what the difference is between them. So let's begin with reflection. So a wave will reflect or bounce off a boundary which it cannot pass through, i.e. a reflective surface. And the law of reflection states that an incident wave angle equals the reflected wave angle. So if a ray of light is approaching a shiny surface at an angle of 70 degrees, it will bounce off that surface at 70 degrees in the opposite direction. Yeah, does that make sense?
It does make sense.
Yeah, and that 70-degree angle is measured against an imaginary line which is drawn perpendicular to the surface at the point of incidence. So basically where the light makes contact, you draw an imaginary line which was normally a dotted line going straight up from the surface, and then as it comes away, and then you measure the angle between the ray and the imaginary line going up the middle. That imaginary line is called the normal.
Which I love. Away from the normal, towards the normal. This is something that you guys should be practicing drawing, by the way. There's like a little toolkit of illustrations you guys may need. If you're doing the Gem A exams, I would recommend being able to draw the law of reflection.
Yeah, it's really important, and it's like something you're definitely going to get asked in exams. It's something you just need to know as a gemologist, basically how light waves operate, and reflection's one of the really important ones.
Exactly.
Perhaps
the next on the list is...
Perhaps we will put some diagrams on the Instagram. That might be a good idea.
Yeah, we should do. Yeah, that's a great idea. I'll add it to my schedule. In the meantime, let's talk about refraction. So refraction, we're back in our Ruby. It is the change in direction of a wave due to change in speed as it passes from one medium to another of differing optical density. So we're back in our Ruby. Light is entering from air. The air is optically less dense than the Ruby, and therefore the light speed of travel slows as it is transmitted through. This only occurs if the light enters the material at an angle. I always kind of think of it as like you're running really fast and then you hit like a wall of goo and like you go, huh! So the light is kind of getting like parlayed over that way. You have another example of soldiers. Why don't you talk us through that one, Simon?
Okay, so I'm imagining a row of soldiers all marching in sync in a line, yeah, and they are marching through long grass. So if they were marching in long grass with their formation parallel to a straight boundary, i.e. head on, of much shorter grass, as they emerge from the long grass, they will increase in speed in unison as they go onto the shorter grass, because obviously it's easier to walk on short grass than it is to be trudging through long grass. Yeah. So if they meet it head on, they're all going to speed up at the same time. However, if they're at an angle and the short grass is, so basically one end of the row of soldiers is going to meet the short grass before the other end of the row of soldiers. Now that means the ones that meet it sooner are going to speed up sooner, which would therefore create a bend or a kink in the formation. And that's sort of, if you can visualize that in your head, you're going to get a fair idea of what happens when light goes from one medium of optical density to another.
Yeah, it's doing its thing, and then it hits.
Does that make sense?
Hits the proverbial wall.
Yeah,
it does make sense.
Exactly. So, and obviously the reverse is true as well. So if you're going from the short grass to the long grass, you're still going to bend as you slow. The example that I've actually written there is actually the wrong way around. So think of it from the short grass into the long grass. Apologies.
I think it's the change in speed is what we're going to focus on in this example.
Exactly. Yeah, that's what we're getting at. There's a change in speed, and which therefore causes a bend.
And the last one is diffraction. So this is the spreading or bending of a wave as it passes through a narrow slit or around an obstacle. Simon, you say here that sound waves bend round corners as they have relatively long wavelength. I had no idea about that.
Yeah, well, so they don't really bend. When I say bend round corners, they don't actually like bend round corners, but because they have quite long swooping S's, then it's kind of like they bend round corners because the S will go they're more beyond the corner as it sort of approaches a corner. So yeah, it does kind of bend round a corner. But actually all it's doing is just waving in a big, long, deep wave.
It's arcing around the corner. Whereas light wave, much more uptight. Light waves have a very small wavelength, which means you have to have a very narrow slit in order to cause them to diffract. But your diffraction spectroscope, that's what's happening. Tiny, tiny slits are splitting the light, which we will talk about in so much more excruciating depth, guys. Don't stress.
Yeah, well, we're going to talk about it in a little bit actually today. So basically, that is fundamentally how waves work, which is really important in understanding light as a wave. Yeah, and light does operate as a wave, which that's probably a bit of a spoiler for the end of the next story. But so sorry about that. So if you didn't know that light bends as a wave, then there's we've taken a bit of the mystery of the story away. But let's get into light theory, a history of light theory. Yeah.
All right, let's set the scene. It is the 17th century. Who is on the case, Simon?
Isaac Newton.
And
The
what is his theory called?
resident genius of the 17th century. Yeah. Now, Isaac Newton's
Yeah.
a pretty brainy guy, and you've probably heard of him. And he's like, what is light? So, however he does it, he comes up with this theory, and it's called the corpuscular theory, which, how the fuck has he done this? But anyway, he's proper smart, this guy, doing all sorts of shit in the 17th century that shouldn't even be remotely possible. But like, here
Apple's
we are.
heads.
This is Isaac Newton. Yeah. He's got his shit together and he knows what he's doing. Yeah. So he comes up with this corpuscular theory, which suggests that light is made up of tiny discrete particles, which he calls corpuscles, yeah, that travel in a straight line as light rays, and that they have a finite velocity and possess kinetic energy.
Okay.
Yeah?
So basically he's imagining almost little blobs that are moving forward, like with their own individual velocity. They are on the move as like groups in rays.
When you think of a corpuscle, what does it look like?
I was imagining some kind of like boil, but
A boil.
should we Google it?
Okay. I kind of
Like a little round globby thing.
I think of like a little ball of marbles or something, like a little bag of marbles. You know, you get those little like string bags of marbles. That's kind of what I have in my head when I think about corpuscles.
So apparently it's like a red blood cell. So we're both not wrong. Globular.
Yeah. Okay. So like back to your botry
So
order,
little
hummocky,
almost like
lumpy. Nice.
Little globby things.
I mean, the word just screams lumpy, doesn't it? Corpuscle.
It does.
So basically, this theory worked on the basis that these particles could reflect off surfaces. Now, Newton had to make some assumptions because he couldn't fully test his theory out. And one of the assumptions was that an external force acted upon the stream of particles, which is known as a light ray, to explain refraction, because his theory sort of, how does refraction work then? And he's like, well, you know, there's an external force acting upon it. Obviously, there was no way of him verifying this in any way. But basically, he was the eminent clever clogs at the time, and people more or less took his word for it because he was pretty much right about everything.
But at the same time, there was a lesser-known genius called Christian Huygens. Did I say that right?
Christian Huygens, that's his name, yeah.
Yeah. And he was exploring a theory that light behaves as a wave and propagates through an invisible medium, which I think this is a great band name, called the luminous ether. And his theory could actually...
ether.
Oh, the luminiferous... gosh, it's even better.
It's even better. It literally is even better, yeah. It's the luminiferous ether.
So
fucking brilliant.
And this theory could justify itself in relation to light's ability to reflect, refract, and diffract, which Newton couldn't do. So Huygens is kind of filling in some of the gaps in Newton's theory with this alternative approach.
Yeah, because basically
Newton,
people could see that light was behaving like waves do, like we've just explained how waves behave. And this theory that light was a wave was supported by the fact that it reflects, it refracts, and it diffracts. Yeah, Newton had none of that. Newton couldn't explain any of that. He had to sort of make some shit up. So
he also got something blatantly wrong, dum-dum, which is he proposed that light would speed up upon entering an optically denser medium, but that is the opposite, Isaac.
Yeah, much like my example with the soldiers, which I completely fucked up as well. So
the difficulty about this, of course,
I'm coming at it from Newton's angle, whereas so that's my justification for getting that fucking backwards.
I often think, so basically the reason why this was so difficult for everybody at this time was because there's no way of measuring the speed of light at this time in history. So you can't do that until 1862. If there was a heaven, I hope that all of the scientists and the seekers are up there and get the answers to the questions that they were trying to solve in their lifetime. Because it just seems so cruel that you have these amazing thinkers operating at a time when, like, today,
you can't prove it.
Who knows? Yeah. Alas. So Simon, carry on.
Yeah. Sorry. Yeah. So basically,
that was I said my piece on that.
Okay, fine. So these two brainiacs, as it were, had put this theory out into the world, and these were widely considered how light behaves for quite a long time. Yeah, and a lot of people were leaning more towards Newton's theory, just basically because he was Mr. Cleverclogs. even though there was less concrete evidence to back up his theory versus Christian Huygens. But he was pretty much right about most things. So it's tricky to argue with the smartest bloke in the world, isn't it?
It is. But in 1862, it had been confirmed that light did indeed slow upon entering an optically denser medium. So sad news for Isaac Newton. But by this time, his kind of corpuscular theory was basically dead in the ground. You know, nobody was buying it anymore. And an upstart brainiac by the name. Go on.
Sorry, I think there's a bit of a delay. So it feels like I'm sort of interrupting you, but I have actually said it already. So I apologise for that.
I won't take it personally.
I was thinking, I was just going to say that the way we've been describing corpuscles, you would think that they are going to, you know, them dying doesn't seem out of the ordinary, does it, considering what they look like in our mind?
Yeah. In my mind, they were dead already.
Exactly.
And oozing.
Yeah, exactly. Something that's oozing isn't going to stick around for very long, is it? That's like
That's never a good sign. So anyway, back to our young man, Thomas Young. The year is 1801, and he threw a spanner in the works, you said in the corpuscles, by proving that light diffracts like a wave.
Corpuscles.
All right, tell me about the double slit experiment. Why can't I read today?
The double slit experience. So we were telling you
the
when we were talking about waves just now.
That's a band name.
Big long sound waves can go around corners, but light waves need to go through very narrow slits in order to disperse. Yeah. So the double slit experiment. Fucking hell. Is basically a way of proving that light operates as a wave. So Thomas Young, 1801, shone a light at an opaque barrier with two narrow slits in it side by side, and then there was a screen behind the slits to record where and how the light hit the screen. So if there were only one slit on the wall where the light is going through the slit and then hitting the wall, you would just see one bright band of light shining onto the screen, yeah? But if you have two slits side by side, you would assume you get two bright bands, right? Because, like, why would you not? If one slit produces one bright band, then two slits would just produce two. Well, no, you don't. What you actually get is a series of light and dark stripes. And this is interference in action.
Because if you guys think about it, so what you're seeing... Go on.
No. I'd said that about
we got to get that
ago.
delay figured out, Simon.
Yeah, no, I don't know what's going on there.
All right. You bring it home.
Okay, fine. So there's two waves overlapping and interacting. Yeah, so constructive and destructive interference is happening right before your eyes here. You're sort of being able to literally visualize the wave function of light. Yeah, so the light areas are where the peaks are aligned and the dark areas are where the troughs are aligned. So you're looking at the wall and you're literally seeing light as a wave function projected onto a wall, which is pretty amazing and was a pretty serious discovery.
And this is exactly what our friend from before was saying, right? Christian. And so the assumption would be that the luminiferous ether must also exist, except it doesn't. So in 1887, a very complicated test known as the Michelson-Morley experiment took place. And with the assistance of a device known as an interferometer, they discovered that the ether does not exist. So in one fell swoop, just like obliterated Newton's theory and opened the doors for Einstein to question what the actual fuck was going on with light.
Yep.
Which led directly to the theory of relativity.
It did, basically, and the birth of quantum physics. So, like, this experiment, which is, like, madness, like, I'm not even going to go into it because it's, like, fucking bananas. And, like, trying to explain it over a podcast is, like, not fucking happening. So we'll leave that one. Unfortunately, I've put that one to one side. But, yeah, basically, Einstein then rocks up. You've probably heard of him too. He's pretty bright. And his theory was that the speed of light is a constant and that space and time are not fixed, right? So space and time must accommodate light rather than the other way around, pretty
mind-blowing if you actually...
No luminiferous ether, I'm afraid.
R.I.P. to the coolest thing that never existed. So tell me about Michael Faraday. So he enters the picture in 1831. He's a self-taught science nerd. What does he discover?
So he made a massive discovery, which is also quite complicated, that magnetism can influence light and is able to rotate the plane of polarized light through certain materials, right? And because of this, it's made a link between light, electricity, and magnetism, and paved the way for another dude called James Clerk Maxwell to... So basically, he took Michael Faraday's theory and put it into words, and like explained it all with a load of bloody maths. And basically bloody maths, and basically surmised that light is actually a form of electromagnetic radiation. So self-propagating electromagnetic waves can travel through space at a constant speed. So this discovery implied the existence of other electromagnetic waves as well, such as radio waves, microwaves, X-rays, and these were all later discovered as well. So this began an avalanche of scientific discovery and is the reason why we have Wi-Fi, telephones, etc., etc. This was the seed of the birth of modern physics, which is all pretty wild.
Yes. And so back to light. It's the early 20th century. Corpuscular theory is long dead. Nobody believes in the ether anymore. Wave theory more or less makes sense. And Einstein enters the fray in earnest with the photoelectric effect. Tell me about it, Simon.
So the photoelectric effect is basically the excitation of electrons by the absorption of light. Now, how were the electrons being excited, you might ask? Well, they're being excited by absorbing discrete particles of light, of energy, sorry. So, what the fuck? They sound very much like corpuscles to me. Like Isaac Newton's literally doing fucking somersaults in his grave. You've all poo-pooed his fucking idea. Einstein comes along and he's like, yeah, I agree, mate. You're absolutely right. Einstein, instead of calling these fucking things corpuscles, gives them a much better name, which is photons. And effectively just pretends that Newton's never said anything.
Never heard of him. But,
don't know what you're talking
so if
about.
you missed the mic drop there, basically what is so wild to me about this story and why I love it is that everyone was right. It's very American. Everybody wins.
Brilliant. Yeah.
Gold stars.
Yeah.
Because basically there's a duality of wave and particle theory, right? So light is both a wave and it's a bunch of particles. It is both, it is all, and everybody was right. So gold stars for everybody.
Yeah, basically. And it's basically just the different interactions with matter which will yield one or another of the properties. So light is either a wave or it's a small packet of energy, now known as a photon, no longer a corpuscle. But basically, it depends what it's interacting with as to how as to which one of those things is at the forefront, I guess.
Yeah. And as we will know as gemmologists, especially if you are doing your diploma, when light interacts with matter, for example, a stone, when it meets a boundary, the speed changes, the light refracts, and the amount that it refracts is known as a material's refractive index. Every material has its own, and this is one of the really great ways that we can identify gemstones. Yeah,
it's basically the most important test. If you can work out a gemstone's refractive index, which is how much it refracts light, then you are a long way towards being able to work out what that is. So light travels at 300,000 kilometers per second in a vacuum, and this would be an RI of 1. Diamond, which has an RI of 2.42, means light travels about 2.42 times slower in diamond than it does in air. Strictly speaking, air has an RI of 1.0003, which is virtually the same as a vacuum. So if we said vacuum and now we're saying air, more or less the same thing, yeah? So air has an RI of 1, diamond has an RI of 2.42, light moves 2.42 times slower in a diamond than it does in air.
Bish, bash, bosh.
Bish, bash, bosh. And then basically when light reaches the boundary between the two media, some of the incident light is either absorbed, reflected, or transmitted. Now, these are important things for you to understand and know about as well.
Very important. So let's start with absorption. So when a particular wavelength of visible light is absorbed, that gives a material its color. So if all of the visible light spectrum is absorbed, it's just like when you're mixing paint. No light is reflected, the item appears black. If none of the visible light spectrum is absorbed, the item appears white or colorless. And selective absorption of certain wavelengths will yield different color results. So, for example, if all of the wavelengths except blue are absorbed, the material appears blue. And it follows logically. So this is what you're looking at through your spectroscope. So you can look at a spectrum, you can understand why something that's absorbing this and this will appear green, for example.
I think the interesting thing here is that kind of tells you that when you look at something and it's blue, it's actually the opposite of being blue, because blue is the color it doesn't want. It's kind of like reflecting that back
rejecting
to you.
it. Yeah.
So like it's not, I suppose you could argue it's actually not blue. It's the opposite, because it's all the other colors. It's absorbing all the other colors. It's like, yeah, I want
and
them.
It's throwing the blue back.
It's like, I don't want the blue. Get rid of that blue. But we would call that thing blue, which is kind of weird.
And color is also dependent on the incident light. So if you're shining a yellow light with only yellow wavelengths onto a blue material, it can't appear blue because there is no blue to be reflected, right? It just doesn't exist. And this is the same question Craig asked us. If you put a stone in a drawer, does it have a color, or does the color only start to exist when you expose it to light and you are there to perceive it? Whoa.
Exactly that. It's like proper far out shit, isn't it?
It's all very existential, I must say.
Yeah, no, it really is. So, whoa, yeah.
Whoa, man.
Yeah.
Now, metals, on the other hand, reflect light so much that they appear shiny. Tell me why, Simon.
So they act like a mirror for electromagnetic waves due to having lots of free delocalized electrons which oscillate and re-radiate the light. So if the metal has a smooth, polished surface, strong reflection occurs, and this is known as specular reflection. Gemstones exhibit some specular reflection and also some diffuse reflection. Diffuse reflection is when the reflected light sort of gets scrambled. So if you can see
Excellent.
like a reflection of yourself in a mirror, for example, which is basically just a shiny metallic polished surface, that's because you're seeing a specular reflection.
Very nice. Now let's talk about transmittance. So this is the amount of light that travels through a material. Glass, for example, is an excellent transmitter, so you're going to get very little light absorbed or reflected. Transparent materials transmit light. That's like a nice little tongue twister for you to just memorize. What do translucent materials do?
So translucent materials transmit and absorb light. So they do a bit of both. And then finally, opaque materials, they don't transmit at all. They either absorb or reflect, or are a bit of both.
Excellent. I'm gurgling.
Don't gurgle.
Must be the appetizer.
Must be.
Can you hear it?
I can actually hear it. Yeah, it sounds like a gremlin.
My dad says I have a floppy epiglottis. I don't know if that's biologically correct.
Yeah, okay. Flopper. That's quite hard to say as well, actually. Harder than the luminiferous ether.
Oh, I love ether.
Luminiferous ether, yeah.
Nice. First novel named.
Brilliant. First novel, first band, first child. Like, what else we naming luminiferous ether?
First puppy, obviously.
You need a cat called luminiferous ether.
Frantz Fanon, Cat Stevens, Spock, and luminiferous ether.
Yeah, perfect. You need another one. Go and get one now. A ginger cat that's going to cuddle down delightfully.
Oh, I almost said deliciously.
Cuddle delightfully. Anyway, we've gone completely off piste, but that's absolutely fine because we've more or less finished.
Yes.
So
let's
that's the
recap.
history of light theory, yeah, and also how waves operate, which is something you need to know. And then we're going to go into a bit more
Remember,
detail
guys,
about
it
how
is
these
a little of everything.
A little of everything, and we're going to try and start breaking things down a little bit more to try and make them make more sense and try and put them into a deeper context for you. So you've got a bit more background info, which is a lot more work for us, but that's fine because
we do it because we love you.
Yes, that's correct.
So get excited because there's a lot more light and optics, but don't worry, we are also going to be peppering through some single family gemstone episodes, some a little bit kind of fun light ones. And of course, we always want to hear about you guys and what you are interested in learning about. We're going to, as we go into exam season, so kind of into December and January, we'll also be talking about our exam experiences, study tips, things like that to get you over that theory and practical exam.
Yeah, I think the exams are towards the end of January, is that right? So yeah, if there's anything that anyone wants, then drop us a message and we can try and do something. We're also going to try and do a quiz, I think, aren't we?
Yes, so we would love to get the Facet Nation community together, either in person or online, for a little Christmas quiz about topics we have covered so far and also any other kind of gemmology trivia that we come across. So let us know if you guys are up for that. And in the meantime, we hope you now have a pretty good understanding of the history of light and wave theory. And that should make our next episode about light and gem testing a little bit more manageable as well.
Yeah, and also it's going to, like, we won't have to necessarily speak so much about how a wave works and how light is and what transmitted means. So we're going to just sort of use these terms as if you understand them in the next episode to try and get the important stuff about the gemstones and how it relates to gemstones and gem testing over to you. So that's kind of why I wanted us to do this, to try and put everything into a context that makes the rest of the explanations a bit more succinct, if you like.
There was one other reason you wanted to do it this way.
Yeah, just because I think it's quite cool. I like it.
Agreed. Hope you guys enjoyed it. We will see you next week.
Yeah,
in the meantime,
thanks to Rob, as ever. Rob's
Yes.
come up big for us, and he's going to be helping us out in a big way when we do our live episode, which is also coming up. So, yeah, if you're coming to the London Gem and Mineral Show, we'll be there on Sunday afternoon. So, yeah, drop us a message if you want to say
4
hi.
p.m. Yeah, come say hi. We have stickers, our first merch.
Yeah, and yeah, I've got a T-shirt now as well, which I will be modelling for the first time at that. So, yeah.
I look forward to seeing it, Simon.
Excellent. I'm looking forward to seeing the stickers. I hope the
All right,
spelling's
we'll
all
see
right
you
on
guys soon. I did actually think about that.
them. Okay, good.
I just copied and pasted. I didn't type anything in them. Don't worry.
Jolly good. Right.
Watch them be like totally off center or something. It's fine.
Yeah.
We're all learning how to use Canva.
It's all good. Yeah. Right. Okay. Yeah. See you later.
All right. Bye, guys.